All right, I'm going to attempt to do some math here. So we are factoring, right? What does factoring mean? It means you take a polynomial, right? And you break it up into two other, polynomials, right? Polynomial, polynomial, polynomial. And of course, the simplest case is just factoring out a number. So we'll start with that. I could have something like f of x equal to minus 10x to the fourth plus 5x 50x squared minus 100. And if I was to factor out minus 10, that would give me minus 10 times x to the fourth minus 5 plus 10. Minus 5x squared plus 10. Now, can we factor this? Could we go further? The 10 doesn't have an x. It's one way to look at it, I suppose. But, I mean, you could hope that this could be factored something like x squared, like that. But it's not pretty, all right? Well, I'll come back to how to solve this kind of problem later, but I'm not going to do it right at the start, okay? So we'll have to come back to this problem later. It's too hard for us at the moment. What I'm trying to say is we'll stop right there for now. Okay, so next example. Suppose we had x squared plus, say, 5x plus 6. Let's try to factor this if we can. So what I'm going to propose we do is we just kind of make a template like that. And then we start thinking about how can we multiply? Have to be 5 and 1. Well, 6. We can either write is 6 times 1, right? It's also minus 6 times minus 1. It's also 3 times 2. It's also minus 3 times minus 2. I mean, these are all different flavor choices. I'm heard of 3 and a 2. And the reason that's a good choice is because 3 times 2 is 6, right? And 2 plus 3 is 5. And that's the kind of arithmetic that has to work out, see, because when we multiply this out, you guys like to FOIL it, right? If you FOIL that, if you want to call it that. We get back x squared plus 3x plus 2x plus 6, right? 3 plus 2 is 5, so that's that. What was the method that I just used? What's this method I just used? How did I pick the 3 and the 2? What's that? No? I mean, the method is educated guessing, right? I mean, there's nothing written in stone that said it had to be 3, 2 here, right? We looked at it, we said, well, maybe 3, 2 will work. We tried it, we multiplied it out to check that it works, right? Every time you factor, you should think about multiplying it back out to check if you're right or wrong, right? If you're wrong, you try something else. Another example, very similar. What if we had x squared minus 5x plus 6? You're okay. Same thing, but with minus. So minus 3, minus 2. Which one comes first, the 3 or the 2? The answer is it doesn't matter. I mean, like if you multiply it this is equal to x minus 2 times x minus 3. So like the order of the factors is immaterial, you know? There's always that ambiguity in all of these examples, okay? How about another one? X squared plus x minus 6. And why did you choose plus 3 and minus 2?
Because if you subtract 3 from 2, you get 1.
Well, if there's also a positive sign before the x and then there's a negative, positive first is going to be a positive and a negative.
Right. Because the coefficient of x was positive, that means the bigger one of the numbers we're using has to get the plus with it, right? If I had, in contrast, x squared minus x minus 6, then what would you do? Negative 3, positive 2, right. Because now we get, and again, like, I haven't been writing this out, but just to double check, that's x times x plus 2, right? Minus 3 times x plus 2, which is x squared plus 2x minus 3x minus 6, which is x squared minus x minus 6, right? What I'm trying to say is, you don't have to write that out, but you should actually think through it. You know? Now, you can think through it with like your FOIL method if you want. It's also fine. But the ultimate judge of any factoring is when we multiply it back out, does it work? I think I've about exhausted this particular example, these numbers. Let's go on to a new set of numbers. Bigger numbers. I'll go with it. X squared plus 101x plus 100.
Oh no, 100, x plus 100, x plus 1.
X plus 100, x plus 1. I think that'll work. Right? What if we had, we get 100 plus 1, x, which gives us 101x, and 100 times 1 is 100. That's the main thing. That's really all you have to check to see if the factoring works, right? Does the sum of the x terms match the middle term, and does the product of the constant terms match your constant? If you have those two things, you're good, as long as we're dealing with x squared in the front. If we have 2x squared in the front, then it gets more complicated. Let's do another one. X squared plus 21x minus 100.
Plus 25 minus 4.
So let's see here. So notice that we're going to get like 25 minus 4 is 21, right? And 25 times minus 4 is minus 100. So I think about those two bits of arithmetic to check whether or not the factoring is right. And I bet that's what you're doing too, right? Yeah. Shall we do another? How about, I don't know, x squared minus 100. So you're like, this is really x squared minus 10 squared, right? So it's the difference of squares. So we do x minus 10 times x plus 10, right? That's that nice special case. We've got a go-to method for this one, right? All right. Let's see, here's another one. X to the fourth plus x squared. Let's factor that as far as we can. By the way, up till now, setting aside my first example, let me number these things. 1, 2, 3, 4, 5, 6, 7, 8, 9. So with the exception of example 1, we have completely factored over the reals, right? You can't go further. You can't break down linear factors smaller than they already are, right? It's kind of like they're atomic in some sense, right? Although we've learned how to split atoms, so that saying has kind of lost its meaning. Anyway, x squared plus 1. Because we can factor out x squared there, right? Now, x squared plus 1, can we factor that? I heard we said no. How do you know no? You said I don't know? Oh, okay. You don't think you can? Well, I can do it. Check it out. So I just take x squared, and I rewrite that as x squared minus the square root of minus 1 squared. Because like the square root of minus 1 squared is minus 1, right? So minus 1 is plus 1. And usually we use the notation square root of minus 1 equals to I. And so this is x squared, x minus I, x plus I. There you go. I factored it. But I had to use something. I had to use complex numbers to factor this, right? You don't have to be a fan. That's not part of this course. But I wanted to show you that's why we can't factor that. To factor that, we would need complex numbers. So this x squared plus 1 is what's called prime or irreducible. It's irreducible, or you could say it's prime. It cannot be factored over the real numbers. You can't break it down further. All right? So we kind of got to be on the watch out for these. If we hit one of these things, we can't factor it if we're just using real numbers. How do we figure out which ones are prime and which ones aren't? I don't know. We're going to have to answer that question, though, right? Or we can just try to factor, and if it factors, then great. And if it's not, there's two possibilities, right? Either we haven't had a good enough imagination to figure out how to factor it, or it's one of these ones that we have to use complex numbers to factor. So unless I give you guys some kind of criteria to judge, you'll always kind of be uncertain about which case you're in, Now your book, I think, puts off that criteria until like chapter 7. I am not content with this. I think this should be discussed much earlier in the course so we can remove this giant hanging question about factoring, when you can factor, when you can't. Because I think students should deserve an answer to that while they're in the midst of all this factoring. So I'm going to do some of the chapter 7 stuff pretty soon. All right? But I'm probably not going to do it right this instant because I know half of you are about to leave. And I don't want to get into a half-hour discussion and you're going to leave in 5 minutes, It's not great. So I'm just telling you that is coming, that will happen sometime soon, probably next class. But in the meantime, we're just going to keep doing these examples, ignoring the elephant in the room, which is, when does this happen? I mean, here's another one. Sure. So this is another example of a prime. And I'm going to answer your question. But like there are other, it's not just x squared plus 1. It can happen with something like this. This is a prime polynomial. If I change that If I change that to a minus 5, then it becomes factorable. You notice, I mean, like, check that out. I'm coming back to your question just a second. See this? A difference of a sign can change it from being not factorable to being factorable. This guy plus 5 minus 5. Plus 5 what? Minus 1, right? So we can factor this one, but I'm telling you, you cannot factor that one with real numbers. Now you asked me what complex numbers are. So complex numbers usually use this symbol for complex numbers, and it's the set of a plus ib such that like a and b are real numbers, and this I is I squared is minus 1. You could also say I is equal to the square root of minus 1. You could think about them as a plane. So if I pick this point here, like 1 plus I, that means I go 1 over in the real axis, and I go 1 up in the imaginary axis. So complex numbers are like in one-to-one correspondence with points in a plane. You can describe all of two-dimensional coordinate geometry using complex notation. Now, are you asking me, like, what are they, or I don't understand the nature of your question yet. I could say a lot of things. So, the reason that we're driven to look at complex numbers, whether we like it or not, is by the end of the course, we're looking at the quadratic formula, all right? And when you deal with the quadratic formula, we end up with the square root of a negative number. That's an imaginary number. So like answers, if you ask the question, what is the solution to the equation? ax squared plus bx plus c equal to 0, like you try to solve that equation, sometimes the answers are complex. Sometimes they're real. The complex answers correspond to the case when we look at the graph, like y equals the quadratic, it's not crossing the x-axis. There aren't any x-intercepts. And that's easy enough to do. You know, you can have a parabola which doesn't cross the x-axis. They come up all over the place in science and engineering. I mean, like, complex numbers are, in some sense, very real. They're as real numbers in a philosophical sense. The terminology imaginary is very unfortunate because they're really, well, anyway. Let me not get off on my complex number rant. All right. Back on track here. Let me erase the evidence. All right. Okay, so everything's fine and dandy, and I think you guys, at least I am usually pretty good at factoring when there's x squared, but what about when there's something like 2x squared? You know, I don't know what should go here. Maybe 7x. How are you going to do that? First of all, let me make sure that I made it not too bad. I may need to adjust the problem, so just give me a second here. So we're going to we'll try putting a 2x here and an x here and see if we can get that to work. That's just an educated guess. It may or may not work. I want to put an 8 here. Yeah. So this is what? 2 times 3, right? So I think if we put a plus 3 over here, that gives me a 6. And then if I put a plus 2 here, that gives me a 2, right? So 2 plus 6 equals to 8. And of course, 2 times 3 equals to 6. So there you go. Now this example is almost kind of, I mean, that's actually a bad way to do this example. What's a better way to do this particular example? What could I do? Yeah, I could factor out the 2, right? And then that's what?
See, that's what I'm always doing. I'm always multiplying 2 out.
Well, but we can't always do that.
I was talking about like you can multiply like as vectors. Like how I did it is I took the 2 out, and then I got x plus 2, and then x plus 2, and then x plus 3. Or whatever.
I think I might know what you're talking about. Let me see if I could talk about it. Let me come up with an example which is a little bit trickier. How about this? 3x squared. Just a second here. I got to put my... So 3x squared plus 11x plus 10. Three x squared plus 11x plus 10. So what? You have a trick to do this?
Yes, sir. You factor out the 3,
Factor out the 3,
and then you go x plus 2, and then x plus 5. And then you get 3x plus 6,
3x plus 6, yeah.
and then it's x plus 5.
Mm-hmm.
And then you get it covers the 3x squared, it covers the 11x, and it covers the 10.
So what are you going to put here in the end?
I mean, eventually you work it out to that. You can, or you can just leave it like 3, and then in parentheses, x plus 2, and then in other parentheses, x plus 5.
I think you'd have to put a 5/3 there, though,
Or you just put 5/3 there.
because I don't think it's going to multiply back out otherwise. I mean, if I put x plus 5 here, right? Then I multiply this out, I get 3 times x squared plus 7x plus 10, which is the 2 plus 5. I foiled.
Oh, no, I'm saying you multiply the 3 to the x plus 2.
But when I multiply 3 to x plus 2, that's 3x plus 6. But what you meant is x plus 2/3. Because you've been taught this super weird slide and divide method, or the too much method, which teaches you bad habits like you can multiply this by 3 and you just put the 3 on the, divide by 3 and you just divide the 2. I strenuously object to this being taught in high schools. I discovered this in the other section. You are not alone. There are 2 people in the other section who've been taught the method that you're using. I can explain it. I've been...
You don't have to.
No, I think I should. So let me take the mystery out of what he's saying for a second. First of all, let me just do the problem. The way I would suggest doing these problems is just write down 3x and x, like make your blank template like we've been doing, but you just put a number here. And then just think through the arithmetic. Do educated guessing, is what I'm saying. That's what I'm advocating, continue the educated guessing when there's a coefficient in front of x squared. That's all I'm saying. I know that's not as like See, the reason people teach the slide and divide thing is because it's more sort of comforting to have this sort of slick algorithm that reduces the problem to the easier problem, right? And my apologies to those of you who don't know what I'm talking about at the moment. I know at least 2 of you know what I'm talking about, sort of. So what would we just say? I got to put 5 over here. Oh, wait a minute, no. I'm a dummy. Come on. I wanted a 2 here, plus 2, and plus 5 here, right? Is that right? The reason I say that is because 2 times 5 is 10, right? And when we multiply this out, we also get like a 5 plus a 6 in the x term, right? So, you know, if I wanted to label what I'm doing, this is the constant, I'm checking the constant, I'm checking the x. And this is my method. It's not very glamorous, but I write down 3x plus something, x times something, and I try to fill in those somethings so that it works. The slide and divide method, it's basically this. So you start with 3x squared plus 11x plus 10. You quote-unquote slide the 3 over to here, which is weird because, well, anyway, that's what you do. And then you take this and you factor it easily, like this. And then you divide by 3, but not really. You do like x plus 5 over 3. No, wait a minute. X plus 5 times x plus 5 over 3. And then whatever you have that one, you multiply that by 3. I'll try to post a video for this not too long. Every once in a while I forget for a day. If I forget to post a video in here for like too long, just email me and say, hey, get on it, you know? And then so magically this becomes 3x plus 5. This, in a nutshell, is slide and divide. Did I do it wrong? I did it wrong. I'm sorry. I was supposed to, I'm an idiot. This was a 6 over 3. I'm supposed to keep the, so I'm sorry. I'll get it eventually. Good grief. Sorry, I don't mean to, I'm trying to give slide and divide. It's just a treatment. And then, okay, great, and then you multiply that one by 3 because that's part of the magical terms and conditions of slide and divide. The reason so, I mean, you're like, well, I really understand that. I mean, maybe somebody in here really understands it. And you're like, I can get the right answer using it. Is it okay? Yeah, of course. But don't be careful not to write down, like if you're going to write those steps down, you should like put them in a box and say, like label hocus pocus beside it or something. I don't know, like I can explain why this works. This is I asked my brother about this, and this is what he came up with. He's like, you take your original polynomial. Let's call that f of x, right? You multiply that by a. That gives us a squared x squared plus bax plus ca. You make a substitution at this point. You let y equal to ax. With that substitution, this becomes a times f of x becomes y squared plus by plus ca. That's that slided polynomial where you just slid the c over to the, multiply c over to the constant coefficient. Then for the problems that you assign you in high school algebra textbooks, this factors nicely into something like y minus r1 times y minus r2. And then what you've got then is a times f of x equals to, well, ax minus r1 times ax minus r2. Then you divide that by a, and you get x minus r1 over a times ax minus r2, which is the slick result that's produced by slide and divide. So there is an underlying logic to it. It's based on a substitution of ax into the polynomial. But you were never taught this in high school. It was just taught to you as a method of like, what was that? Was that Battleship? I feel like that was a Battleship.
I was waiting for the explosion.
Did I, whose Battleship did I sink?
Oh, I've got some. I was over here. I was saying, put some eyes on the board.
Oh, okay. But, I mean, I don't know. I'm sure I'm going to regret showing you guys this after I leave class today, because I don't think this helps you much. But I'm just trying to explain, there is a method, there's a logic behind the slide and divide, but the reason I wouldn't teach it is because I don't want to do all that. And unless I do all this, I'm teaching you guys to do weird stuff like multiply just one number in a polynomial. And that isn't how it works, right? When we do 3 times the polynomial, we have to multiply the 3 times everything, distributive law. So like slide and divide, it's very bad. It's unteaching distributive law. Oh, Sorry. Some of the things that are being taught in high school right now, it's like, whoa, why? Because this is not that hard if you just do educated guessing. Let's do more. So how about, you been moving? Oh, you moved, okay. You've been moving. How about, oh, let me do one. 3x squared plus 31x plus 10.
Wish they had like a calculator that you like talk to, and then you say what you've done and stuff. They should make one.
They do make one of those.
Are you for real?
Yeah.
You just talk to it? How much is it? Nah, not the phone. I'm talking about like a calculator. I said that stuff on my phone pulled me some bullcrap. Like this?
Factor 3x squared plus 31x plus 10. No, I didn't quite do it right. It's got me solve 3x squared equals 31x plus 10. That ain't what I want.
You just talk to it?
I tried.
Yeah. See, it always gives me some.
Factor 3 times x squared plus 31 times x plus 10. Khan Academy. Take your Khan Academy.
I'm telling you, it never worked for me. I wish they just had a calculator so you could just search the web. Just boom, there it is.
Interesting. I mean, I'm quite certain if you just go to the trouble of typing in factor 3x squared plus 31x plus 10 into like any number of math help sites like wolframalpha.com or something, it'll do it. But apparently it's not so. I'm pretty sure that if you take a photo of it, like photo math will do it. I should not tell you guys about these things.
I've had photo math and
It doesn't help.
nothing ever works for me. 3x plus 1 x plus
3x plus what?
1.
X plus 10? Okay. Yeah, you see where I come up with that from the other example. You know what I'm up to, don't you? Okay, so just do another one of these. Let's see here. How about 5x squared plus something plus 2 I'll do a minus 2. We've been doing too many pluses. Let me put a minus there. 5x squared minus 4x minus 2. So to get this minus 2, we need like a minus 1 times a 2 or a 1 times a minus 2, right? So pretty much the natural choices are to either put minus 1 or to put 2, minus 1 and 2 or 1 and minus 2. I mean, which one? Again, assuming I haven't messed up the problem and given you something that's prime. Hey. I mean, I usually just try something. Plus 1, minus 2. I think we got a, oh, ouch. Oh yeah, I think I didn't think through this one right. I meant, did that say 4? I think I'm not done writing. I don't think I'm done writing. That was a 9. That was a minus 9 right there. Sorry about that. Yeah, you're not allowed to change problems like that. But, you know, it's one of the rights and privileges of being a math instructor. You can change problems midway. Or we could start working out the problems on your formula sheet if you like. I think I've probably done enough at this point for you to get the idea, I think. So that's a plus x, we get a minus 10, so 1 minus 10 is minus 9. All right? So, great. Now, I will go back to the formula sheet here pretty soon, but there's one other big idea which we need to talk about today. Big idea is factoring p of x completely makes solving p of x equals to 0 easy. So we have not solved any equations. What is this factoring business we've been doing? I've written a bunch of equals here and there, but my equalities, they're doing what? They're linking one expression to another expression, right? This expression to that expression, right? So the answer to a factoring problem is an expression, right? In contrast, when I look at an equation, p of x equals to 0, I'm actually looking for numbers that when I plug it in, it works, right? So the key idea here is that if a times b is equal to 0, then that means a equals to 0 or b equals to 0, or of course it could be both, right? So when I have something like x squared plus 3x plus 2 equals to 0, and I can factor that like this, I can think about this as being a and that as being b, right? And so this means that either x plus 1 equals to 0 or x plus 2 equals to 0, right? Which means what? X equals to minus 1 or x equals to minus 2. Notice that there's a plus 1 here, there's a minus 1 there. There's a plus 2 here, there's a minus 2 there. So the numbers which appear in the factors are, you know, minus what you see in the solutions because of this algebra. There's always this trade-off. Like in contrast, if I had x squared minus 3x plus 2, I would get x minus 1 times x minus 2. If I set that equal to 0, then I could tell you the solution is x equals to 1 and x equals to 2. And we can go back, and we can look at every one of the examples today, pretty much, and we can solve the corresponding equation easily, because we already factored, right? Once you've factored, solving the equation is piece of cake, right? Like if I go back to this example over here, right? If I had another colored chalk, it would help. See if I can find one. Well, I got green, I got orange, and I got blue. I wonder which one's going to work best. What do you think? I think the orange. Equals to 0, right? You got, it's got me? So if I add equals to 0 here, right, which is a new problem, it's not the factoring problem anymore, now it's the solve problem. What is the solution? Exactly, x equals minus 1 or x equals minus 3. How about this one? What if I set this equal to 0? What's the solution there? Well, this one, x equals minus 2. But how about this one? What do we get from that? How do you figure out? You just put 3x plus 5 equals to 0, right? Mm-hmm. So, you know, kind of annoying when there's a number out in front, but we can still do it just like that, yeah? I mean, another way you could do it would be like this over here. See this one? I know you guys aren't going to like this, but check this out. I could say 3 times x plus 1/3 times x plus 10. See what I did there? See what I did? I factored 3 out. I mean, if you do that, it makes the solving step way easy. So x equals minus 1/3 or minus 10. We good? All right. So let's see if we can solve some problems in here. Can I erase? Is it? I didn't believe that. That was suspicious. Oh, I realized there's one other thing. There's 2 other things with factoring I should talk a little bit about before I move past factoring. So the one is quartics. I'll start out with the quartic trick. So if we had something like x to the 4th plus 3x squared plus 2, we could look at that as like x squared is playing the role of x, and see if we can factor like that, right? So I think plus 1 and plus 2, I think, is what to do here. So basically think about x squared playing the role x did. If you have a quartic, that usually will help you. Or you could have something like this, x to the fourth minus 625. So what's 625? It's 25 squared. So we have what? What I'm doing right now, it's kind of similar to exercise 5 on the formula sheet. It actually is pretty similar to that problem. But this one kind of comes at it from a different angle. Yep. I do. And again, yeah, is the one with polynomials? I think you have it. So I look at this as like a squared minus b squared, you know? And so that's x squared minus 25, x squared plus 25. So x squared plus 25 is just like x squared plus 1. We can't do anything else with that. That's prime, right? But the x squared minus 25, hey, that's a difference of squares again, right? That's x squared minus 5 squared. So this is x minus 5 times x plus 5 times x squared plus 25. And there you go, we've factored it completely.
Boom.
Yeah, boom indeed, yes. Okay, so those are that's basically the main trick for like a fourth order one. Now, I already told you about the difference of perfect squares formula, right? So a squared, we just used it, right? A squared minus b squared is a minus b times a plus b. Obviously, this should be on your formula sheet, you know? But there is also a corresponding difference of cubes formula. What's a cubed minus b cubed? Well, it's a minus b. Starts out the same. It would be cool if it was a squared plus b squared. It's not quite that, but you're not off that far. That's part of it. See, because we think about multiplying that out. We got back our a cubed. We got back our minus b cubed. Great. But we've also done what? We've also got a minus ba squared, right? And this one also gives us a plus ab squared. And to fix that, I believe what you got to do is add ab here. If we add ab there, I think it all works out, because then you get like a squared b, but that subtracts with this, and you get a minus ab squared, but that adds against that. And so when you multiply that out, there you go. This is one of the quote-unquote special form trinomials. There's also a formula for a cubed plus b cubed. What would that be? I think that one's a plus b. A squared minus ab plus b squared, I think. I got to check on that. I get back my a cubed. I get back my b cubed. I get a plus ba squared. I get a minus ba squared. I get a plus ab squared. I get a minus ab squared. I think we're good. So there's the sum of cubes formula. You're like, okay, that's lovely. Well, how does it help us? Well, for example, What if we had like x cubed plus 8 and you wanted to factor it? If you knew this special,
Take the x over to cube root of 8.
right? That's that is yeah, cube root of 8 cubed, which is what? I mean that is 2 cubed. The point is 8 is 2 cubed. But you're right. We could, generally speaking, take a number. If the number wasn't pretty, if we had like x cubed plus 17, then you would do the cube root of 17 cubed. Don't ask me what the cube root of 17 is.
So we ain't actually got to get you, we just got to put that.
Well,
To actually give you.
it would not give me joy to grade the one I just writ, the one I just writ, yeah, writ, the one I just wrote. Like, I don't find myself putting that on one of your tests.
Okay.
I prefer this one because that one has whole number answers and.
I didn't want to have to break down the 17.
Okay, well, I'll erase it from the record. But this one, we have a equals to x, right? And b equals to 2. So just, this is what? And for reasons that I can't explain yet, I happen to know that this cannot be further factored. That's actually prime. Because of the secret math I haven't told you yet. Chapter 7 stuff. What if we had, let's see here. I'll do another one. How about x cubed minus 64? So here I'm identifying, this is like x cubed minus 4 cubed, right? 64 is 4 cubed. And so I do x minus 4. Wait a minute. Yeah, x minus 4. Then x squared minus, wait a minute, plus 4x. Yeah, plus 4x plus 16, I guess. I'm just checking it. All right, so let's try to work some of these problems. What do you say? Did you guys try to work out? Let's do number. So let's do exercise 14. 14 is 14 s to the 4th minus 33 s squared plus 18 s squared. This one's kind of silly. Supposed to factor that completely. Exercise 16. I'll do 15 as well. Here you've got v squared plus 18 vd plus 81 d squared. This one's just kind of weird. Exercise 16, this one's easier. V squared minus 36. The instruction for all of these is to factor completely. example, let's see here, exercise 17. We're supposed to factor w cubed plus 125. Exercise 18, we've got 64 minus 125 v cubed. I'm really kind of annoyed with your book in the sense that there's so many problems here without x's. I mean, I like there being a given, a problem here or there without an x, but I tell you, it's really, I would be happier if there were more x's in these problems, because I think, unfortunately, changing the letter just, makes it a little bit more tricky. It shouldn't, but I think mentally it does for people who are still just learning. Exercise 20. We've got 4s squared minus 36. Exercise 21. 7, finally an x to the 6th, plus 128. Oh, wait a minute, just 28. 28x to the 4th.
What kind of bug?
Yep.
Did you give your life to Pakistan?
Give my life for Pakistan. I mean, why? Is this some sort of like risk quick guess? Like talk about playing a game of Risk or something? Like,
No. You ready to give your life to Pakistan?
am I ready to give my life for Pakistan? I don't have any particular allegiance to Pakistan that I know of. I mean, I think I've had some Pakistani friends at various points in my life, I'm pretty sure, but any particular reason?
I'm about to show you.
Uh-oh. I may regret asking. All right, let me start carving my way through these problems. You guys got the first one? So like this first one here, the reason I said it's silly is like you should really just take the squared terms and put them together, right? So we've got minus 15s squared there, right? And then what can we do in terms of factoring this one? Not much, right? I mean, I can pull an s squared out. Uh-huh. Yep. Now, I guess I could factor that further if you wanted me to.